it's magic red light, and it's counting, right? And now it says like 159. Okay, thank you for the sentence there. Yes, okay. All right, so today we are going to look at the time-independent Schrodinger equation. As in, we'll keep things relatively simple, relatively. I don't like this chalk. This how to just use this little piece of chalk. The time-independent Schrodinger equation. Okay, since I'm writing a title here, I'll not say Shrek. Schrodinger equation, and that's another thing that gets really tiresome to write after a while. So sometimes I may resort to calling it the TISE, T-I-S-E, time-independent Schrodinger equation. So what we're going to do is find a way to get rid of the IH bar deciding T part and only worry about the spatial parts of the equation. So if we go back to the time-dependent Schrodinger equation, that's what? What's the time-dependent Schrodinger equation? The time piece is blah, 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 blah. What multiplies deciding T? And I'm also going to follow this often used convention that the full time-dependent solution is a capital Greek psi, and the time-independent a solution of the time-independent equation is a small Greek psi without the little on top and the bottom. What multiplies the deciding T usually when we write the time-independent Schrodinger equation? IH bar, yeah, I mean we could throw it to the other side if we wanted, but IH bar deciding T is equal to minus something over something else. H bar squared over 2m. Some d what did it what's that derivative? Yeah, the second derivative. I'll capitalize the psi. Second partial derivative of psi with respect to x. So d squared psi dx squared said sloppily. Plus what else? Times, yeah, we still have psi, making our life happy, and I'll explicitly write psi of x and t there. So we're assuming v is independent of time. In general, v could depend on time, but in many problems, v is time independent, and so we'll assume that here. And in fact, if v is not time independent, then there's no point in trying to make the time independent Schrodinger equation. We want a spatial only dependence for v. So we want to solve that equation right there. If v does not depend on t, we can use good old separation of variables. In other words, we look for solutions that have the following form. They factor into a time-dependent piece times a space-dependent piece. So we look for solutions of the form big psi as a function of x and t is equal to psi of x phi of t. So some function of x times some other function of time. Does that mean that we're going to find a general solution in this form? No, it's not true that every solution has that form. But on the other hand, it turns out that the general solution can be written as a sum of terms of this form. And so that's what's useful about this, is we'll get something which can be generalized. You can add up solutions that have this form in order to get the general solution in principle of the time-independent Schrodinger equation. infinite sum of those terms of that type in order to get the general solution. So, any questions so far? All right. So, in terms of little psi and phi there, we can say that, wow, I'm still kind of, I mean, it's a nice big piece of chalk and all that, but it just doesn't have a good feel to it. So I'll try it for a while, but we'll see. Maybe you guys really care, but I don't know, whatever. I'm blathering. It's a blathering kind of day. We have that d psi dt is equal to what? D big psi dt is equal to, in terms of little psi and phi there. Yeah, the partial derivative with respect to t doesn't care about psi of x. It's a constant as far as it's concerned. And then we get a total derivative of phi with respect to t because t only depends on t. So the partial derivative is the total derivative. So that'll be psi d phi dt, suppressing the variables attached to the functions there. And similarly, if we take the second partial derivative with respect to x of the total space and time dependent wave function, then that doesn't care, the derivative with respect to x doesn't care about phi, it's a constant for it, but on the other hand we do get the second total derivative of psi with respect to x squared. And little psi, remember we're distinguishing between big psi, which is the full time dependent x and t, and little psi, which only depends on x. And then phi is a constant as far as that differentiation is concerned. So then we plug these two expressions back into the time to full time dependent Schrodinger equation to get that I bar little psi d phi dt is equal to minus h bar squared over 2m d squared psi dx squared, and that's not sloppy saying it anymore because I really do mean the second total derivative with respect to x of little psi times phi plus v times psi times phi. And next we do something which is entirely standard when doing separation of variables, and that is we divide by the function itself again, written in the form little psi, little phi. So divide through by psi phi. Psi phi. Star Trek, Star Wars. You get I h bar times 1 over phi d phi dt on the left-hand side there. Because we divided through by psi phi, so the psi's cancel, and then you get 1 over phi d phi dt. And then on the right side, when we divide by psi phi, the phi's are going to cancel, and you get 1 over psi d squared psi dx squared. So we get minus h bar squared over 2m. 1 over psi d squared psi dx squared plus v after we divide by psi phi. And the thing to note here is that on the left-hand side, there's nothing that depends on x. So the left-hand side depends only on t. And the right-hand side has nothing that depends on t. All the things in the right-hand side are functions only of space, of x. So the right-hand side depends only on x. questions? But we can do better than that, because if this is to hold for all x and t, the only way that's going to work is if, in fact, neither side depends on x or on t. In fact, both of these have to be constant. The only way this can hold for all x and t is if both sides are in fact constant. Now note, that's not saying that psi is a constant and phi is a constant. It's saying that 1 over phi d phi dt is a constant, and that 1 over psi d squared psi dx squared is a constant, so that the time dependence of 1 over phi has to cancel the time dependence of d phi dt. The time dependence of 1 over psi has to cancel, the x dependence of 1 over psi has to, in combination with v here, cancel the 1 over the d squared psi dx squared. So the only way this can hold for all x and t is for both sides to be equal to the same constant. And it's very important to be sure that you understand the argument as to why that is. The argument is that otherwise, suppose we fixed, held constant t, let's say, and varied x. So we're going to hold t constant, and we're only going to change x. Well, if I hold t constant and I change x, the left-hand side, would that change? No, because it only depends on t, right? So as I varied x, the left-hand side has to stay constant, but these things are equal. So the right-hand side also has to stay constant. So therefore, the right-hand side can't change when I vary x either. And you can make the exact same argument if you were to fix x and vary t. So, why? If we fix x, and, well, I guess I started with I fixed t and I varied x, right? So I'll fix t and vary x. If we fix t and vary x, the LHS, left-hand side, I'll often say LHS meaning left-hand side and RHS meaning right-hand side, the LHS will not change. But then the RHS cannot change, comma, either. If I hold t fixed and I vary x, by first principles, the left-hand side can't change because it doesn't depend on x. But since they're equal to each other, that means the right-hand side can't change either. So the right-hand side also doesn't depend on x. Similarly, if we fix x and vary t, blah, 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 rather than write the rest of it out, blah, blah, blah means, you know, same deal. Either way, you conclude that, in fact, neither side can depend on x or t, because otherwise you break the equality. Because it has to hold for all x and for all t.
So you have to vary both t and x simultaneously.
But even then, they're not going to change.
Oh, really?
Because if I vary x, nothing happens. If I vary t, nothing happens. Therefore, nothing happens. These things are both constants over the entire xt plane. You know, you could if I plotted this as a function of x and t, it's a flat line. It's a flat plane everywhere. Because varying x doesn't change anything at any point. Varying t doesn't change anything. Therefore, nothing changes. You cannot vary. They're both constants.
Derived from a very variable equation in and of itself.
Yeah. Right. So, on the assumption that we can in fact find solutions of this sort, it'll have to be true that both of those things are equal to constants. Despite their apparent dependence on x and t, in fact they don't depend on x or t. Psi and phi themselves do, but those combinations do not. Okay, any questions? So we're going to call the so-called separation constant, the thing to which both these sides are equal, E, capital E. And the reason is because it's going to turn out to be the energy of the system. So inspired by what those who have gone before us have already figured out, we'll use that to say, okay, let's call the separation constant E, because it's going to turn out that it's going to be the energy. Call the separation constant E, because it will turn out to be the energy. But at this stage, it's just, we don't need to know that now. We just need to know it is a constant, and that's just the name we're giving. So now, if we look at the right hand, the left-hand side, that's got to equal the separation constant. So 1 over h bar, I'm sorry, stop it. I h bar, I'm talking to myself. I h bar 1 over phi d phi dt. This whole involved conversation with them. Stop it. No, you stop it. No, me stop it. No, I will. No, we will. I don't know.
Yes, you and me. Yeah.
Something like. Okay, so I h bar 1 over phi d phi dt is equal to constant E. So that says d phi dt is equal to minus I e over h bar times v. Where did the minus sign come from? Why is it minus? Yeah, I did a 1 over I there. I divided by I, and remember that 1 over I is minus I. So I could have written E over I h bar phi, but let's leave the i's in the numerator. So minus I E over h bar phi is equal to d phi dt. So the derivative of phi with respect to time is a constant times phi itself. That's something that you should have seen before. It's a very standard differential equation. This says, I need a function whose derivative is a multiple of the function itself. What kind of function has that property? Exponential functions have that property, right? Derivative of e to the t would just be e to the t, and the derivative of a constant times, derivative of e to a constant times t is the constant times e to the constant times t. So the kind of function which is essentially its own derivative times a constant is exponential functions. So this says phi is equal to e times, e to the power of minus I e t over h bar. Now you say, well, you could have a constant out front. Yeah, you could, but we're going to attach that to psi instead of phi. Any constant out front, because the solution is a product of psi and phi, any constant out front, we can absorb that into psi. The constant out front can be absorbed into psi. Because if I take the derivative of e to the minus I e t over h bar with respect to time, what's d phi dt? Minus I e over h bar e to the minus I e t over h bar. So it works. This is in fact a solution of the differential equation. If I take the derivative of this, I do in fact get minus I e over h bar e to the minus I e t over h bar, but that is phi. That piece is phi. So if you just be explicit, minus I e over h bar, e to the minus I dt over h bar, but e to the minus I dt over h bar is phi again, so in fact d phi dt is minus I e over h bar times phi itself. So voila, the time dependence must be of the form e to the minus I dt over h bar. Okay. Any questions? This chalk is kind of quasi-erasable. I must push hard. I'm definitely going to get better chalk in between periods. This stuff must be from the chem department. Oops. She's going to tell on me now. Yeah, right. Yeah. Hey, this is the physics room you're in here. We designed this room. Yeah. Well, no, we didn't put the chalk in here. Must be other people carrying it in here to our perfectly designed room. And then if we look at the other side of the equation, minus h bar squared over 2m d squared psi dx squared plus v psi plus v, sorry, is equal to e. Both sides of the equation are equal to the separation constant. So the left-hand side was minus h bar squared over 2m d squared psi dx squared plus v times 1 over psi. I'm missing that very important piece. 1 over, so minus h bar squared over 2m, 1 over psi d squared psi dx squared plus v is equal to e, the separation constant. So multiply through by psi and get that we will have obtained a solution that is separable if psi obeys this equation. Minus h bar squared over 2m d squared psi dx squared plus v psi is equal to e psi. Okay, here's a trick question for you. What's the solution of that equation? I'm asking you a question which you can't possibly answer because it depends on the form of. No? You have to apologize. I forgive you. It depends on the form of v. Yeah, you can't tell me what the solution of this is until I tell you what v is. And for most v's, you still can't tell me because it's unsolvable. But for certain important v's, it is solvable. So, for example, for the infinite square root potential, you can solve it analytically. We're certainly going to do that. I know how much you love that. And then, even better, we're going to solve it in 280. We waved our hands a little bit with this. Here we're going to do it in detail. We're going to solve it for the best potential ever, namely the harmonic oscillator potential, the harmonic oscillator potential. But this is, in fact, that's the time-independent Schrodinger equation right there. So that's the point, is that we've done separation of variables. So if we can solve this spatial equation, we tack onto it e to the minus I dt over h bar, and that's the solution of the full-time dependent Schrodinger equation. But it's not the only solution. We're not done, because any solution of this form, and generally there's an infinite number of solutions of the time-independent Schrodinger equation here, can be tacked onto a corresponding time-dependent piece, which depends on the energy, and then you add them all together to get the general solution of the Schrodinger equation. So it's a glorious infinite sum. Okay, any questions? So our task for a while is going to be solving this one-dimensional time-independent Schrodinger equation. solving a differential equation, not only do you need to know what the equation itself is, but you need to know boundary conditions. You need to know properties of the function and maybe of its derivatives on, say, the endpoints of the interval in question. Generally, boundary conditions allow solutions for only certain discrete values of E. In other words, I put an arbitrary E into this equation. I can always solve this. Well, okay, I have to be careful. Okay, so I'm being the physicist here. I'm sure a mathematician would come along and say, well, not if blah, 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 pathological, blah, 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 pathological. Okay, get out of here. We can always solve this for any E, but in general, for an arbitrary E, the solution will not satisfy the boundary conditions. Generally, you find that only specific values of E give you solutions which not only satisfy this equation, you find a psi that satisfies this equation, but also has the right properties, value of the function and of its derivatives, on the boundaries. And since E, even though we haven't showed this yet, since E represents the energy, that means only certain energies will be allowed. The boundary conditions will mean that only certain energies are allowed. And in 3 dimensions, this gives rise to the hydrogen spectrum, spectrum of other atoms, only certain energies are allowed, etc., etc. But it's important to realize that that doesn't come from the Schrödinger equation itself. It comes from the boundary conditions imposed on the Schrödinger equation. So the way I like to put that is, it is the boundary conditions which put the quantum into quantum mechanics. And it's really important to understand that fact. People can get confused and think the Schrödinger equation is why you get quantized energies and so forth. No, it's not enough. It's the boundary conditions which cause the quantization.
I thought it was the Planck constant, because that's a big one.
Well, it's related to that. But in free space, in general, a particle can have any energy you like. But it's when you've got a potential around that's imposing boundary conditions that you get discretization of the energies and so forth. So it's the boundary conditions that put the quantum in quantum mechanics. Well, any questions? And from a historical perspective, another thing that students often aren't clear on is they'll think that quantum conditions, quantization was discovered when quantum mechanics was discovered, and that's simply not true. It's the other way around. Even in classical physics, you have met quantized systems. So for example, suppose that I have a string which is tied on both ends. Then you know that only certain so-called normal modes of vibration are allowed for the string if both ends of the string are tied so that they're not allowed to move. And so there's this condition that the only allowed normal modes have the property that an integer number of half wavelengths fits from one end of the string to the other. Now, is every possible motion of the string represented by one of these shapes? No. You can have some very complicated motion, but that function that represents the general very complicated motion can be written as a sum over normal mode motions. So the normal mode motions represent the separable solutions which can be added together to describe an arbitrary state of vibration of the string with both ends fixed. Schrödinger and his contemporaries knew all about that kind of quantization of classical systems. Boundary conditions, in general, mathematically put quantization conditions on their solutions. And the point was that experiments were showing that systems behaved as though only certain energies were allowed to them. And that's what suggested to the pioneers of quantum mechanics that matter has a wave-like nature, because they already knew from classical physics that systems that are described by waves, by partial differential wave equations, exhibit quantization. And they said, oh look, systems are behaving like they're quantized, just like classical wave systems are, so maybe matter itself is described by a wave. And that was the motivation for coming up with wave mechanics, the idea that particles, that matter has dual particle and wave nature, was that they already knew about quantization from wave equations classically, and then they adapted it to the new physics of quantum mechanics. It wasn't that quantum mechanics was invented in order to discover how to make systems quantized. People already knew about quantized systems, it's just that they were classical systems. Okay? Any questions? All right. Now, why do we interpret this as the energy? I said before, I was misspeaking, really saying, we'll show that it's the energy. I mean, we're not really going to show it's the energy. We're going to state that it's plausible that we ought to interpret the separation constant E as representing the energy. And then, through various examples over time, it becomes more and more so that, yeah, that's what we would consider to be what we ought to call the energy of the system. But in particular, we've already mentioned before the basic identification that leads us to do this, and that is, remember that we said that the P operator is represented by minus IH bar partial with respect to x, and the x operator in the so-called position basis, where the wave function is written in terms of space and time as opposed to momentum and time, the position operator, the x operator, is just multiplication by x itself. And so if we look at what we have on the left-hand side of this equation, minus h bar squared over 2m d squared dx squared plus v operating on psi is equal to E multiplied by psi, where E is a constant. So in other words, I've written this as an operator equation where I've symbolically added minus h bar squared d squared dx squared plus v and applied them both to psi to produce E times psi. Well, minus h bar squared d squared dx squared in one dimension, if psi is only depending on x, this partial derivative is the total derivative. And so this is equal to the P operator squared over 2m. Because the P operator squared is two applications of minus IH bar partial with respect to x. And so that produces minus h bar squared over 2m d squared dx squared. So P operator squared plus v psi equals E psi is what the one-dimensional time-independent Schrödinger equation becomes. And the P operator squared over, well, P squared over 2m, again, we said it before, P squared over 2m represents the of a classical particle, kinetic energy of a classical particle, suggesting that this is the kinetic energy operator. And in fact, by definition, it is. This is the kinetic energy operator, P op squared over 2m. That's the kinetic energy operator. And V itself is just the potential energy operator. So the one-dimensional time-independent Schrödinger equation, written as an operator equation, is kinetic energy operator plus potential energy operator applied to psi is E times psi. So this whole beast on the left-hand side is the energy operator. And remember that we have this terminology, and again, we've said it already in here. If you've got an equation which says an operator applied to a function gives a number times the function, then the function is said to be a blunkety-blunk of the operator, and the corresponding number is called the corresponding blunkety-blink. So what's the blunkety-blunk? Yeah, we're talking eigenfunction, eigenvalue, right? If you have an equation of the form, I'll just write generically, if I've got some A operator times a function f is a number times that same function, then f is said to be an eigenfunction of our operator A with eigenvalue little a. So that A there is supposed to be just a number. 7, if you have units. 7 potatoes per kiloparsec or whatever. It's just, but it's, I want to see that. Anyway, so this equation right here is saying that psi is an eigenfunction of the energy operator, and that E is the eigenvalue. And in quantum mechanics, the whole idea is that the eigenvalue of an operator is the value of the physical quantity you're going to get on a measurement if the wave function is an eigenfunction of the operator that represents that quantity. Here, this operator represents energy. This is saying we want psi to be an eigenfunction of the energy operator, and the corresponding eigenvalue is the energy. So that's why we interpret E as being the energy of the system. Now it's up to experiments to decide whether there's anything physically tenable about all that. That if we do all this, it makes predictions as to what we'll measure when we actually interact with systems, and if that'll be reasonable to call that thing energy and so forth. And of course, if the answer to that was, no, that doesn't happen, we wouldn't be having this class, would we? So obviously, it turns out that yes, it's very reasonable to call that the energy. Okay, any questions? So now, we assert, without proving, and in fact, for most systems, we'll see, for most operators, we can't prove that their solutions form what is called a complete set, but if it weren't true, quantum mechanics would fall apart, and so we just figured, well, quantum mechanics hasn't fallen apart yet, so even though we haven't come up with a general mathematical proof, it seems like it better be true. The idea here is that, in the physicist sense, any function psi that satisfies the boundary conditions arbitrarily can be written as a sum of solutions of this equation. And so the idea is that the solution to the full time-dependent Schrödinger equation, the one with the IH bar d psi dt in it, solution to the full time-dependent Schreck is big psi of x and t is a sum over all possible values of n. We might arrange things so that n could be 1 to infinity, but in some problems it's more natural to n also take on negative values or maybe only odd values. So I'm being kind of generic here. N equals 1 to infinity, or really just overall n of Cn psi n of x e to the minus I e sub n t over h bar. In other words, in general, you get an infinite set of psi sub n's that satisfy the time-independent Schrodinger equation. You attach the corresponding time dependence, e to the minus I, corresponding energy t over h bar, times some weighting constant, add them all together, and that will be solution of the full time-dependent Schrodinger equation. So the Cn are constants. To find the Cn, we need to know psi of x is 0. In other words, we need to know the shape of the wave function at times t equals 0, or t equals 1, or t equals minus 4,433 million years ago, whatever. You have to have some time where at that instant you know what the wave function is everywhere in space. It turns out if you know that, you can figure out what the Cn's are, and then you know the entire solution because you just attach the Cn's to all of these pieces and add all of those infinite pieces together, and there's your solution. Now, of course, in practice that might be a little hard to do. In practice, you probably have to make a finite truncation, but Mathematica can let you do that. And also it's the sort of thing where if you're a little hazy on that now, doing examples firms that up in your head. But the idea is then the general solution is typically an infinite sum of solutions of the time-dependent Schrodinger equation multiplied by time-independent Schrodinger equation multiplied by the corresponding time dependence e to the minus I e sub n t over h bar. So the psi n's are the solutions of the ties for the e sub n's that allow the boundary conditions, the BCs, to be satisfied. You've already seen this sort of thing in action before. We're going to go through all of this again, but just as a quick jump ahead, you may recall for the infinite square well, where we represent that like a picture like that. The potential goes to infinity everywhere outside some region. It's 0 inside that region. What do the wave functions look like? What do the allowed wave functions look like?
Like standing wave?
They look just like standing waves on a string, yeah. So the allowed wave functions are, there's a ground state, lowest allowed energy, which has 1 hump. There is a first excited state, which has 2 humps, 2 antinodes. There's a second excited state, which has 3 antinodes, and so forth. Each of those has a different energy. Only those energies allow you to satisfy the boundary condition that psi is going to 0 on the boundaries of the infinite square well. So there's a certain discrete set of energies that are allowed and corresponding wave functions. Does that mean a particle in a square wall always has to have one of these wave functions? No. In general, the wave function is a sum of wave functions having that form, each with its own private time dependence. the higher the energy, the faster it wiggles, the faster it shakes, because the complex exponential here is really what we can consider a trig function, because it's, remember that e to the I theta is cosine theta plus I sine theta. So this is really a trigonometric time dependence with time. So these are a bunch of, these guys are all wiggling. The shorter wavelengths wiggle faster than the longer wavelengths do. So if I knew the shape of the wave function at some particular instant, like initially the wave function, say, looks like that. I've magically managed to make the wave function start like that, satisfies the boundary conditions, finishes on the ends. I can use this to calculate what all of the CNs are for all of the different standing waves that can exist with well-defined time dependences inside, well-defined exponential time dependences inside the well. So this snapshot lets me figure out in principle what the wave function looks like at all later times by calculating all the CNs and then plugging into this expression. Now, generally that's more of an in-principle kind of thing than an in-practice kind of thing, but in principle you can do it. And even if it's not the infinite squirrel, even if something much more obnoxious, you can still, in principle, do it. And of course most things are much more obnoxious, but part of physics is figuring out how to simplify. Yes?
So you say you can reproduce that so much as a
I sure
by
can.
just changing and moderating the constants
Yeah.
and add.
For a suitable choice of these constants, I can duplicate any function I like that satisfies the boundary conditions. For the case of the infinite square well, what I'm really doing is saying something equivalent to Fourier's theorem. In other words, an arbitrary function can be written as a sum of sines and cosines. I'm writing this as a sum of these sine waves inside these boundaries here. So really the CNs in that case are just Fourier coefficients. You just find the Fourier series that represents this function. You find the CNs in the Fourier series, and then you just do this infinite sum. Because you have a super powerful brain, and that's, or really, or you tell Mathematica to do the first 1,000 terms in the sum for 7 seconds or whatever, and make a plot, then that's what happens. So in that case, it's just a Fourier series. But in quantum mechanics, we go more general than that, because sines and cosines are convenient things to use to represent functions, but they're not the only complete set. Sines and cosines aren't the only set of functions around which can be added together to create any arbitrary function that you like. And in general, solutions of the time-independent Schrodinger equation form complete sets. For the infinite square well, there's a convenient Fourier set of functions, but in general, they're weirder looking things that nevertheless, taken together, can be added to produce any arbitrary function. Is there a question back here? Okay. And it's absolutely crucial to the interpretation of quantum mechanics that these solutions be complete sets, because the idea is going to be that when you make a measurement, so if the wave function is of one of these forms, the system has a definite energy, and so I'm guaranteed to get that energy if I make a measurement. This wave function, however, doesn't have a definite energy associated with it, because it is a sum of wave functions with definite but different energies. That means if I measure the energy of this beast, I don't know what I'm going to get. But it turns out that the probability of getting energy E sub n is the absolute square of C sub n. It's Cn star C. So this expansion gives you the probabilities for all the values that you might get for measurements of the energy. Well, if for an arbitrary case of what the potential energy looks like, you didn't get that the solutions formed a complete set, you wouldn't be able to make a sum like this. You wouldn't be able to interpret quantum mechanics in terms of probabilities and all that. Everything would go out the window. So even though we've never proved mathematically for arbitrary potentials that the solution is always a complete set, quantum mechanics won't work if it isn't. So from that standpoint, we physicists know it has to be, and that's our proof, quote unquote, is because quantum mechanics is right. Now, do we know that quantum mechanics is right? No, but it works awfully well, so we're